This second lecture is called It's Just a Phase, and it's going to introduce you to the idea of phase change and also heat transfer. It says sometimes you go through a phase whether you like it or not. It's a good piece of advice. So the learning goals for this particular chapter are that students will understand the various phase transitions and the energy change required to change phase, and they will be able to differentiate between the three different types of heat transfer. So we look at our next one. What's going on there? It says phase transition graph. It says the heat can be added with no change in temperature. So we saw that in the first lab that we did, that we added a lot of heat here. This is on a burner and still there was no temperature change. And what the energy is doing is just going into changing the phase or changing the potential energy of the atoms. And so these are the common phase changes. You have solid to liquid and liquid to solid. Whenever you have, it's called fusion or freezing. That tends to be when you go from a liquid to a solid, and that requires a loss of heat. It's an exothermic transition, and because of that, it's a negative Q value. Whenever you're melting, on the other hand, you're moving from a solid to liquid. It requires heat input. That's called an endothermic transition, and it has a positive Q value. And what you should know is that the heat that's required to fuse is the same magnitude as the heat that's required to melt. So if I take 10,000 joules to melt, I have to take 10,000 joules out of it to make it fuse. And so they're kind of analogous to one another. They're mirror images of themselves. A gas to a liquid is called condensation. If you're moving from from a gas to a liquid, and if you're moving from a liquid to a gas, it's called vaporization. A lot of times it's called boiling. Same thing as the solids and liquids. It's got the same amount of energy just going back and forth. One's endothermic, one's exothermic, and you need to just be aware of those. You also have gas going to a solid. A lot of people don't realize that a gas can go directly to a solid or a solid to a gas. But when a gas goes directly from a to a solid, it's actually called sublimation, and that requires loss of heat. There's usually a change in pressure also. And then when you move directly from a gas to a solid, it's called crystal lattice formation. And you see sublimation with dry ice. What you see here is you see something that's a solid block and it's turning into gas. Crystal lattice formation you generally don't see very often, but it's just the opposite of it. You take a gas and all of a sudden it's a solid. It skips the liquid phase. And once again, it's the energy required to sublimate is the same as it is required to crystallize. Okay, so you do need to know those phase changes and kind of the direction and whether it's endothermic or exothermic and those sorts of things. Next, you have the equation for changing phase. We had Q equals Cm delta T whenever we were talking about a change in temperature. We use the formula Q equals Ml when we're talking about a change of phase. Where Q is still heat, M is still mass, but what's new here is this L term. And this L term represents what we call the latent heat of transition. And that's going to be different for every substance and every phase change. So it's the energy that's required to change a particular phase from something to something else. Okay, so it says it is possible to vary the pressure and temperature such that an equal amount of ice, water, and vapor are present in a sample. This is called the triple point. It says compare the velocity of the particles in each particular phase. And so here what you're trying to say is they are all at the same particular temperature. So they're at the same temperature, and if they're at the same temperature, temperature is a measurement of kinetic energy. Kinetic energy, they're all the same particles, so they have the same mass, and therefore they should have the same velocity. And so that's kind of difficult for people to say because they're saying what the solid is moving just as fast as the gas. In this one particular case, that would be the case. Example 2, it says how much energy is required to convert 5 kilograms of 100C water into 100C steam if the latent heat of vaporization for water is 2260000. So we're going to use the equation Q equals ml, okay, where Q is the heat. And we're going to say, okay, the mass is 5 kilograms. The latent heat of transition is going to be 2260000. So you would say 5 times 2,260,000. And when you multiply all that out, you get a very, very large number because the energy required to change phase is much, much higher than it is to change temperature. And you would get something like 11,300,000 joules, which is quite a bit of energy. So realize that whenever you're talking about a phase change problem, you're going to have a lot more energy than you're used to dealing with whenever you have a temperature change question. Next, it says how much energy is required to heat 10 kilograms of ice to 50 degrees Celsius water. It says the latent heat of fusion for water is 334,000, while the specific heat of water is 4,184. So this is actually a two-step question because we want to convert it from 0 degrees Celsius ice to 0 C water to 50 C water. Looks like we forgot the W there. So here, in this particular thing, what I want to do is I want to change the phase. And here, I want to change the temperature. So this is actually going to require two equations. I need to change the phase using Q equals ml, and I need to change the temperature using Q equals Cm delta T. C. So we'll go ahead and start it. We'll say the first thing I want to do is change the phase, and I have 10 kilograms of a sample. So I would say Q equals 10 times the latent heat of fusion, which is 334,000, and that would take care of my Q equals ml. I would also do equals the same mass times the specific heat of water, which is 4184, times the temperature change, which I'm going from 0 to 50, so it's 50 degree temperature change. And you would take all those, you would multiply them out and add them together, and the energy required to take 10 kilograms of 0C ice to 10 kilograms of 50C water would be about 5,432,000 joules. Now we also learned in the first unit that objects tend to move towards thermal equilibrium. So heat is transferred from high temperature to low temperature. And that was by James Joule. He was the first one to discover it, and that's why the unit of energy is named the joule. But let's go ahead and take a look at it in more detail. In the lab, we said we had a cup that was surrounded by air. It should move towards equilibrium, and it didn't. So the foil covered cup has a lower temperature than the saran wrap covered temperature, and we wanted to explore the reason why. And a lot of people speculated on the fact that this is covered right here actually prevented the sun from shining on it, and the sun provides heat, and that might be the difference. And if you were to look at that, that is most likely the case. There are three different methods of heat transfer, and the sun is one of them. So let's go ahead and take a look at all of them. And the first one, which is the easiest one, is conduction. Conduction is the transfer of heat by any two objects that touch. So you see that whenever you brand a cow, you're putting something that's in direct contact. There are two different temperatures that are in direct contact, and because of that, you have a very efficient transfer of heat. Okay, if you take something of different temperature, directly touch it to something else of a different temperature, there's going to be an immediate transfer of heat. You can avoid the transfer of heat, or you can mitigate it whenever you're looking at something that's an insulator. What an insulator is something that slows down the conduction of heat by preventing direct contact. Now, insulators come in lots of varieties, but they tend to, number one, individual molecules absorb a lot of heat. Okay, so it can take in a lot of heat without changing its temperature, so it doesn't pass that temperature change on to the other side. So water is an excellent insulator. Okay, also empty, like a vacuum, is also an excellent insulator because it doesn't allow the conduction of heat. Empty space, like you hear, coolers are hollow. We used to call them coolers. They're really insulators, but they're hollow as well. So anything that can absorb a lot of heat and not transfer it to the other side would be an insulator. And you see that insulators are in your house. You tend to see them in the rafters, but they're also in the walls to prevent the heat or the cold air from being transferred from one side to the other. The next one is convection. Convection is kind of a special case, and it's where higher temperatures, whenever you have something that has higher temperature, remember it can move more, so it tends to move higher up in the atmosphere. Okay, things that are colder don't have as much energy, so they tend to not be able to escape gravity as well, so they tend to fall. And so you have cold things that fall, and then you have hot things that rise. Well, that's a method of heat transfer as well, where you have warm air rising and cold air falling, or warm water rising and cold water falling, and that's actually called convection. Now, convection is actually really useful because it's what creates that circular motion in the water. Whenever you heat the bottom water in a pan, you're not just heating the bottom water. The hot water rises to the top and it circulates, and your whole pot becomes the same temperature. This is also one of the primary mechanisms by which you generate weather patterns. Okay, whenever you have thunderstorms, it's because you have hot air and cold air that mix, and whenever they mix, there's these kind of violent turning as the hot air rises and the cold air falls. So convection is actually very useful. Is that your oven is generally called a convection oven because what it does is it heats the air. The air rises and it heats the food. It cools down and comes back down and is heated again, and the warm air rises. Okay, whereas if you were to look at conduction, conduction would be the top of your stove. You're putting the pan in direct contact with it and the food in direct contact with the pan, so the food tends to be heated by conduction whenever you're using the stove top. But whenever you're using the oven, it's done by convection. The last method of heat transfer, and the one that was relevant to our lab, was that of radiation. Radiation is the transfer of heat that does not involve matter. It is the only one that can go through a vacuum. The sun heats the earth via radiation because there is no molecules to transfer the heat in between. So radiation is sometimes called infrared radiation or radiant energy, and we'll talk about infrared radiation a little bit later in the semester. But you should know that radiation is generally not as efficient as conduction because it just doesn't transfer heat as well. But it is the only one that does work in a vacuum. So it says, why is it more dangerous to put your hand above a candle than to the side? So if you were to put your hand right here, you wouldn't get burned. Okay, you would still be exposed to somewhat radiation, and you would be exposed to some conduction from the air, but air is a very, very good insulator, so you wouldn't get a whole lot of conduction that way. But if you do put your hand over the candle, you're exposing yourself to not only the radiation, but you're also exposing yourself to the convection. The warm air wants to rise and would come into contact with your hand. So putting your hand to the side of a candle isn't really going to burn you, but if you put it directly above, it's much, much, much worse. It says, what method of heat transfer is prevented by placing double-sided foil on the rafters of roofs? And so you have to remember that this double-sided foil is actually a reflective barrier. And since it is a reflective barrier, what it's doing is it's taking and it's the infrared radiation, or the radiation comes in and it bounces off as a result. Okay, so it's there to prevent the radiation heat. Now, when you put this stuff down right here, this stuff right here is called insulation. It's there to prevent the transfer of heat by conduction. And whenever you have fans that are in your roof, you tend to have a fan, and what that is there to do is there to transfer the heat out by convection. So you have all three methods of heat transfer that you're trying to regulate whenever you're trying to make a home more energy efficient. It says determine 3 ways you can prevent the transfer of heat from outside to inside on a hot day. The first and most obvious one would be that you would want to keep the doors closed and the windows closed because that would not allow for the transfer of heat into the doors. You can also use all the methods that we talked about here, but some other ones that you can do is you can actually put special foil on the windows, not foil but tint, and that tint would prevent the transfer of heat by radiation. So you close off the house, you don't let it open, so that prevents the transfer by conduction. And then if you have fans that are there, those fans can be used to pull the heat directly up and out of the house, so it avoids the circulation that you could get by convection.